A $50 million attack helicopter does not give you 3 times the speed of a $16 million one. It may not even give you a bigger helicopter. So where does another $30 or $40 million actually go? There is one complication before we answer that. Military helicopter prices are messy. Some figures are close to the cost of the aircraft itself. Export contracts can also include spare engines, sensors, training, weapons, support equipment, and years of logistics. So treat the prices in this ranking as approximate markers, not 10 identical invoices. Even with that warning, the gap is enormous. At roughly $16 million, the cheapest helicopter here already gives its crew armor, guided weapons, advanced sensors, and one of the strangest emergency systems ever fitted to a rotorcraft. By the time the price passes $50 million, the expensive part is increasingly difficult to see from the outside. Crew survival, night fighting capability, maintenance, environmental protection, software, sensors, and eventually the ability to receive information from aircraft and units miles away. That is what this ranking is really about. Not which helicopter has the longest specification sheet, what governments are actually buying with the difference. The Ka-52 Alligator gives itself away before it ever leaves the ground. 2 large rotors sit on the same axis, turning in opposite directions. Most helicopters use one main rotor and a smaller tail rotor to counter the twisting force produced by the main rotor. Kamov took another route. Its coaxial layout uses those counter-rotating main rotors to cancel that torque without a conventional tail rotor. The result is the unmistakable shape of the Alligator. Inside, the layout is unusual again. Most dedicated attack helicopters put the pilot and weapons operator one behind the other. The Ka-52 seats them side by side inside an armored cockpit. But its most remarkable feature appears only when everything has gone wrong. The Ka-52 family is one of the very few helicopter designs equipped with a crew ejection system. That is a far more difficult proposition in a helicopter than in a fixed-wing aircraft. There are several fast-moving rotor blades directly above the people who need to get out, so the emergency sequence has to clear an escape path before the seats can leave the cockpit. The Ka-52M also carries the sensors, cannon, rockets, and guided weapons expected from a modern attack helicopter. But listing every missile would miss what makes this aircraft memorable. At the lowest price point in this ranking, engineers were already spending money on 2 uncommon decisions: a coaxial rotor system and an emergency escape capability almost nobody else attempted. The next Russian helicopter looks far more conventional. Its expensive problem begins when the sun disappears. The original Mi-28 program goes back to the Soviet era, but the Mi-28N was shaped around a requirement that became increasingly important for modern attack aviation. Night could no longer stop the mission. Its layout is classic for the category. The weapons operator sits in front. The pilot sits higher behind. A single main rotor does the lifting, while a tail rotor handles torque. The narrow forward fuselage is heavily protected around the crew. None of that is especially exotic. The important equipment is what helps those 2 people operate when their own eyes are no longer enough. Thermal and optical systems support navigation, observation, and targeting in darkness and poor visibility. On later configurations, radar adds another source of information beyond what the crew can see through the canopy. That matters because night flying in an attack helicopter is not simply daytime flying with the lights turned off. The crew may be moving close to terrain while simultaneously tracking navigation, threats, other aircraft, and whatever is happening on the ground. Then they still have to identify what they are looking at. The Mi-28N carries a prominent 30mm cannon and guided anti-armor weapons, but those weapons are useless if the crew cannot first locate and understand the target area. So its $18 million story is not about adding another gun. It is about keeping the gunship useful after visibility has collapsed. Ka-52 stands out through unusual mechanics. The Havoc spends more of its identity on what the crew can detect. At number 8, physical size becomes a poor guide to cost. The WZ-10 has a maximum takeoff weight of roughly 7.8 metric tons. That makes it lighter than several helicopters already on this list. Its importance comes from a different design era. By the time China developed the WZ-10, an attack helicopter was increasingly expected to do more than fly out, search on its own, fire its own weapons, and return. Information had become part of the mission. The WZ-10 carries electro-optical equipment for observation and targeting, along with systems that allow information to be exchanged with other elements of the force. That capability is easy to underestimate because there is no dramatic moving part to film. A cannon can be photographed. A missile hanging under a wing is obvious. A communication link is largely invisible. But consider what it changes for the crew. If another platform already has useful information about an area, the helicopter may not have to begin every search from zero. Coordinates, observations, or other mission data can reach the aircraft from outside. That means some of the helicopter's value now lives behind the cockpit displays. Processors, antennas, sensors, software, communications. None of those make the WZ-10 look physically larger. They make the aircraft more connected. At $22 million, this is where the price ladder begins moving from obvious hardware toward capability hidden under the skin. 4.6 metric tons. For the A129 Mangusta, that number is more revealing than its maximum speed. The Italian helicopter is dramatically lighter than machines such as the Mi-28 or Mi-35, yet its designers still had to fit 2 crew members, protection, sensors, fuel, guided weapons, and the equipment required for day and night missions into that limited mass. Weight becomes a budget of its own. Armor protects the crew, but armor weighs something. Extra fuel extends endurance, but fuel weighs something. Weapons, wiring, sensors, cooling equipment, and electronics all compete for the same margin. On a much heavier helicopter, engineers have more room to absorb those decisions. The Mangusta never had that luxury. That is why simply calling it a small attack helicopter misses the engineering problem. It was one of the first dedicated attack helicopters developed in Western Europe, and it had to deliver useful anti-armor capability without growing into the weight class of the heavy Russian machines. Modernized versions gained better sensors and broader weapons integration, which made the same basic constraint even harder, adding capability without allowing the airframe to become something completely different. The A129 does not win this list with brute force. Its $25 million lesson is packaging. How much combat equipment can be integrated before a lightweight helicopter stops being lightweight? The next aircraft tackles cost somewhere completely different, not in the air, on the ground. The most useful number attached to the AH-1Z Viper is 85%. The Viper shares roughly 85% of its major components with the UH-1Y Venom. That sounds less dramatic than a missile. For the U.S. Marine Corps, it can matter every single day. 2 aircraft with different missions can share engines, major dynamic components, elements of their rotor systems, maintenance knowledge, support equipment, and parts of the same supply chain. Now imagine the alternative. Every unique component needs its own inventory, its own maintenance procedures, its own training, its own path through the logistics system. Multiply that across aircraft operating from expeditionary bases or ships, and complexity becomes expensive very quickly. The AH-1Z itself was a major evolution from the older Cobra family. The two-bladed rotor of earlier versions gave way to a four-bladed system. Avionics, sensors, drivetrain components, and mission equipment were heavily modernized, but those upgrades only explain the aircraft. Commonality explains part of the fleet. A combat helicopter spends a large part of its life with panels open and technicians around it. Components have limited service lives. Inspections happen. Parts wear. Something eventually needs replacement. A military, therefore, pays for more than the machine's performance during one flight. It pays to generate the next flight. The Viper's $32 million story is about reducing the amount of completely unique infrastructure required to make that happen. Most dedicated attack helicopters are built around two people and the weapons surrounding them. The Mi-35M has room for 8 more. Behind the cockpit is a troop compartment, and that one feature changes the logic of the entire aircraft. The Hind family was never a perfectly pure gunship. It combines attack capability with internal transport space, allowing the helicopter to move personnel as well as carry substantial weapons outside. That creates an obvious compromise. Every cubic foot of cabin volume occupies space a dedicated attack helicopter could use differently. Every passenger adds weight that might otherwise become fuel, protection, or weapons. A more specialized machine can optimize itself around one job. The Hind accepts inefficiency in exchange for flexibility. That becomes useful for militaries that may not have large numbers of specialized helicopter types available for every mission. The same airframe can transport a small group of personnel, provide armed support, move casualties, or operate as a gunship. The Mi-35M modernized the old Hind formula with changes aimed at reducing weight and simplifying operation. Its shorter stub wings are an obvious visual difference, and fixed landing gear removes one mechanical system that earlier versions had to retract and extend. But none of those details are as memorable as the cabin itself. At $36 million, the Mi-35M spends part of its performance budget on something the helicopters around it largely abandoned: internal space. While the rest of the ranking becomes increasingly specialized, the Hind stubbornly remains two kinds of helicopter in one fuselage. The number that defines the Rooivalk is not its speed. It is 12. Only 12 production aircraft were built for the South African Air Force. That is a brutal number when development costs have to be spread across a fleet. A dedicated combat helicopter requires years of engineering, testing, specialized tooling, flight trials, software, training, support equipment, documentation, and parts. Build hundreds and those costs can be spread widely. Build 12 and each aircraft represents a much larger piece of the program. But Rooivalk was not simply an expensive curiosity. South Africa developed it around conditions its forces expected to encounter: heat, dust, long distances, remote operating areas, and a support environment very different from a large permanent European base. That affects systems that rarely make the thumbnail. Turbine engines need protection from dirty intake air. Cooling becomes more important as temperatures rise. Maintenance requirements matter differently when a large workshop is not sitting just beyond the flight line. For years, those capabilities existed mostly as potential. Then the aircraft finally went to work. In 2013, 3 Rooivalks deployed to the Democratic Republic of Congo as part of the United Nations mission there. The type flew its first combat mission that November, nearly 3 decades after development had begun. That operational debut gives this section something a brochure cannot. The helicopter was no longer being judged only by test data or design intent. Aircraft, crews, technicians, spares, and support systems all had to function away from home in an actual deployment. Rooivalk's $40 million position is therefore less about one spectacular component than two expensive realities. It was specialized for a demanding environment, and almost none were built. More than 100 airframe modifications, over 1,500 new parts, around 250 electrical cables. Those are the figures Airbus gave for converting a French Tiger from the older HAP standard to the more capable HAD configuration. From a distance, it was still obviously a Tiger. Under the skin, a great deal had changed. The HAD brought more powerful engines, a higher allowable takeoff weight, updated targeting equipment, and compatibility with additional guided weapons. And France was only one customer. Germany's UHT followed a different configuration. Australia operated the ARH. Different nations wanted different weapons, sensors, communications equipment, and mission requirements built around the same basic helicopter family. That sounds simple when reduced to the word variant. It is not. Change a major sensor, and it has to communicate with the rest of the aircraft. Change a weapon, and software, wiring, interfaces, testing, and certification can follow. Then every configuration has to be maintained for years after the engineering team has finished modifying it. The Tiger also accumulated operational experience in very different environments, including deployments to Afghanistan, Libya, the Central African Republic, and Mali. One episode from the Sahel in 2019 shows how far helicopter crews sometimes have to stretch a platform beyond the neat role written on paper. After another helicopter went down during a French operation, a Tiger used an emergency extraction procedure to carry 3 crew members away from the area. That does not explain $44 million by itself. It does something more useful. It shows the difference between designing versatility on paper and having crews depend on it far from home. With the Tiger, complexity became expensive because several countries kept asking the same airframe to become different versions of itself. The T129's problem begins before the helicopter even lifts off. The air itself can take performance away. As altitude increases, air density falls. High temperature reduces it further. For a helicopter, that matters because the rotor has less dense air available to generate lift, while the aircraft may still be expected to carry crew, fuel, sensors, protection, and mission equipment. Turkey specifically required the T129 ATAK to perform in hot temperatures and at high altitude. That requirement helps explain why simply calling it a Turkish version of the A129 Mangusta is misleading. The family resemblance is obvious. The mission system is much less so. Turkey incorporated its own avionics, electro-optical equipment, electronic warfare systems, communications, and weapons integration while adapting the platform around local requirements. That electronic warfare equipment gives the crew warning of several kinds of threat, while the targeting system supports observation and engagement during both day and night operations. But the important point is not another list of electronics. It is why those systems had to coexist inside a relatively compact helicopter that was also expected to retain useful performance in demanding climates. The T129 is an adaptation program. Instead of beginning with an empty sheet of paper, Turkey started with an existing design and changed the parts that mattered most for its environment, mission requirements, and domestic systems. That is a different path to an expensive helicopter. You are not paying only to build the airframe. You are paying to make an existing airframe behave like somebody else's helicopter. At number 1, that process has been happening for decades. More than 5.3 million flight hours. over 1.3 million of them accumulated in combat. Those numbers are more useful for understanding the Apache than another argument about maximum speed. The AH-64 family has been operating since the 1980s, and the AH-64E Guardian represents what happens when decades of field experience keep forcing new capability into a proven basic design. The familiar silhouette remains. Two crew members sit in tandem. A 30mm cannon hangs under the nose. Weapons are carried on the stub wings. But the modern Apache increasingly revolves around information. Sensors help the crew build a picture of what is happening around the aircraft. Longbow radar on equipped helicopters adds another way to detect and track activity. Digital communications allow information to move between the Apache and the wider force. Then there is manned-unmanned teaming. On modern AH-64E configurations, the helicopter can work with information from unmanned aircraft instead of relying entirely on what its own crew can see. That changes the scale of the problem. The two people inside the cockpit still have only two sets of eyes. The aircraft around them does not have to. Information can arrive from sensors positioned somewhere else. That is becoming increasingly important because the environment facing attack helicopters has become more complicated, not less. A modern helicopter may have excellent armor and powerful weapons and still face serious threats if it enters the wrong area without enough information. Protection, therefore, cannot rely only on making the aircraft physically tougher. Awareness matters. Coordination matters. Knowing more before getting close matters. The Apache's price also demonstrates why military aircraft numbers require context. In January 2026, for example, the United States approved a possible Israeli package for 30 AH-64Es and extensive related equipment at an estimated $3.8 billion. That is not $3.8 billion for 30 bare helicopters. And that distinction is the entire point of this video. By the top of the ranking, the aircraft is only one part of what is being purchased. There is the helicopter. Then there are the sensors, the communications, the software, the training, the spare parts, the maintainers, the support equipment, the upgrades that will arrive years later, and the larger network the aircraft is expected to join. At $16 million, the Ka-52 was already a sophisticated armed rotorcraft. At more than $50 million, the Apache shows how far the category can move beyond the airframe itself. From $16 million to more than $50 million, the biggest surprise is how rarely the extra money simply buys more horsepower. The Ka-52 puts unusual engineering into its rotors and crew escape system. The Mi-28N spends heavily on fighting after visibility disappears. The A129 shows how expensive capability becomes when weight is tightly limited. The Viper attacks the ownership problem through 85% commonality. The Hind trades specialization for an internal troop cabin. Rooivalk carries the financial penalty of extreme specialization and a fleet of only 12. The Tiger shows what happens when one helicopter keeps being re-engineered for different customers. The T129 takes an existing platform and reshapes it around a different country, climate, and mission system. And the Apache pushes the category further into sensors, communications, unmanned teaming, and a support network much larger than the aircraft itself. So if you controlled the next $10 million, where would you spend it? Keeping the crew alive? Keeping more helicopters ready to fly? Or giving the crew better information before they ever get close to the threat? Tell us which one matters most to you. And subscribe to Megamass for more machines built around problems ordinary hardware was never designed to solve.